We are here to go on with the Silq stuff. Because last time I left it, I think was in Grover's, right? Like I left it in Grover's. So I've got a bunch of kind of trying to clean up as well, and I'm still a bit torn apart. I really want to move, all my stuff to StrangeWorks at some point, but it feels like a bit limited in terms of all these little other quirky things, right? Like I've got like a quirk checked out here because I'm working on a couple of custom gates that I'll talk about in another video. I've got the Quantum Dojo and the Silq test that I was playing with as well here. So, and I think where did I leave these? So this is uncompute. No, that's not. I think that's none of the stuff that is just the test. That's actually not Grover, right? Because if I remember well, I think I was going through Grover as being the example. How can I find this comparison to Q sharp? Examples. Where's Grover? Functions debugging type. Here. Oh, so there's some content, some new stuff in here.
Silq is a new quantum programming language designed to abstract from low-level implementation details of quantum algorithms. In contrast to existing quantum languages, Silq supports a descriptive view on quantum algorithms that expresses the high-level intent of the programmer. As a consequence, Silq algorithms are significantly shorter and simpler, less error-prone, and modify the program's quantum state according to an intuitive semantics that follows the laws of quantum physics.
Okay.
Silq's key technical novelty is a quantum type system that captures important aspects of quantum computation.
That's interesting. So quantum type system. So M3, it's got to have to do with measurement, something constant, something Q free. That's got to do with and computation, right? I think.
And enable safe automatic uncomputation,
Okay.
a fundamental challenge in existing quantum languages. Silq's development environment enforces static safety and even includes a simulator, so check it out.
Okay. Let's go back to Grover's algorithm because I wanna. Where was I? So we went through the basic feature stuff. We went through conditionals. I feel like it's been quite a while. I'm gonna have to refresh a little bit. If H. So what this is doing is applies the Hadamard to the wire Y and then kind of overrides Y with that. I wonder how you would do a multi-control, like if it's like if X and I don't know, Q or something like this. That'll be just a Grover's algorithm in Silq. Yeah, so we went through these here and we said, okay, so there's a number of iterations, blah, 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 and then there's this is an array of n candidates because we're doing it's the general Grover form, right? We're trying to find n things. Is it? No, n is qubits. Okay, n is just the amount of qubits. So you've got n candidates. No, you've got 2 to the power of n candidates, right? So you've got n qubits, and then what you're doing is, okay, so you have, I don't know why they use C and or can for candidates. It's a bit confusing. But the first one is creating the uniform superposition. But it's a funny thing because it doesn't come across as you're creating a superposition. That is one thing that I find weird in this language, or in the way that it's expressed in here, right? Like I'd expect or I would imagine a superposition being an actual resource or an actual concept, but here it's just an array of something. And I guess qubits, right? Like, I mean, Is it an array of integers? So it's an array of integers. That's kind of weird, but it's initialized at 0. And then and then you're applying the Hadamard. Okay, so that prepares you the initials proposition, and then you do the iterations, and so you have the function that's the oracle. So you just do it like that with a line of code. And what basically this is already implicitly doing is it's phasing by pi each of the candidates that fulfill the function f. I guess f goes something that takes the superposition, which is const. F is constant, or the superposition is constant. F preserves the argument. Okay, but um, mm, there's a lot of uh, you see the point. The thing here is there's a lot of stuff that seems to be um, it's like the code is short, but it's a lot of stuff that's happening implicitly that I don't know if you should keep that in mind or not, or is it just because what are you phasing, right? Like that statement just says phase pi, but like, is it something that's phasing what? Like, what is this phasing? Like this, I take a look at the code, and I don't know. Like, it's not like making reference to candidates, other than I know that it's in the context of these if f candidates, right? So I really don't know what is this phasing. Does this thing actually have an API documentation or sort of an actual language documentation that I can explore? Annotations, types. Okay, so there is booleans. So const. An addition const indicates that a variable will not be changed in the given context, but it does change, right? Like Grover takes. So wait a second. So Grover is a function that what it does is it takes an array of qubits and it outputs a boolean or what? No, it takes a function. Okay, so that the whole parameter is a function that goes from a superposition um, to a boolean, and it does so without changing that. That's what this is saying. And sorry, I forgot. I'm not at home right now, and I forgot the pen. But I could try. I could try to do it by hand. So this is what's constant. So this is what the function is not modifying, which it bothers me a bit because it does modify the phases, right? But then like the effect of these is, so there's got to be then something here. If this is something native from the language, there's going to be phase. Okay, phase, yeah. So what is it doing? So these are functions, built-in functions. Phase R multiplies the phase of the current state. Okay, so there's the concept of a current state. So that's the point. There's the concept of a current state that's global to what you're doing or what? Current state by, sorry. Yeah. By e to the power of IR phase only has an observable effect if it's executed in a quantum conditional. Which is what's happening here, right? Only has an effect if it's in a quantum conditional. Why? Okay, because otherwise it's like applying a global phase, I guess. That's what this is saying. Yeah, I guess. returns a duplicate. Array, vector, quantum indexing. Silq also supports quantum indexing E1, E2 for non-classical. What? Does not contain any classical components, non-classical types, function types, or array types. Really? Okay. So what do you just get? Like you can index an array with a superposition as an index? That's funky. Okay, so you let's go ahead. Let's maybe see if that gets explained. I understand. Okay, I kind of understand this, but I still have a hard time understanding that the program keeps track of a state. Or is it just the program has just one state? I guess that's the point is you run a program in Silq and you're just dealing with a quantum system within a program. You cannot have multiple quantum systems within a program. So this affects the whole state. So there's some sort of internal thing. There's an internal, mechanism that keeps track of the state, and I don't know. What if I just want to apply? What if I just want to apply a phase to? I guess can I say if, and then I can reference qubits and say if qubit 1, I will try. But first, let's get Grover's working, okay? Generic parameter and classical types. I don't remember where I left. Constant Q-free functions. So another intrusive destroy superpositions. Exactly. Okay. So Q-free meant that it does not destroy or introduce superpositions. In particular, is F. If F takes as input a basis state, then it will return a basis state. Yeah. Okay, but because it takes a superposition, it's Q-free, so it doesn't destroy the superposition. It means it just phases it. That's what this Q-free is saying here. But it's still at the same time constant. But I'm not sure if what's constant is the superposition or the function. F preserves argument. No, it preserves the argument. That's, yeah. Function consists of classical operations. Okay. Q-free constant parameters for Q-free functions. Note that X is Q-free, that while X is Q-free, it does not preserve its argument. It consumes its input. In contrast, the argument of F is annotated as constant, indicating that F preserves it. Concretely consider the state where it captures possibly entangled remainder of the state, then running on this state where F is Q-free yields that preserves the original summoned expressions and augments them with an additional value. I don't know. Superpositions, line strength result in a state 5 forward can halts the equal superposition of all n-bit integers. That's a bit weird. Like you have to. This seems to be like written as an array. That's what's weird. So it halts a superposition, but it's like it feels like that's an array structure. So that's just confusing. Loops, conditionals, Grover's division operator. Okay, so we left, I think, preventing errors, reverse measurement, using consumed variables. Come on. But you're not giving me the Grover's diffusion operator. Completing the explanations of our example, line 8 applies Grover's diffusion operator to can Grover diff. It increases the coefficient of solution, obtaining blah blah blah, and decreases the coefficient of non-solutions. After one loop iteration, this results, or is it something that is it already built in here? No. Doesn't seem it's an actual function of the language. Then maybe we could just try to do it, right? How do I make these symbols, man? Even these, I just might hard code that and try it because maybe let's just try these. So I will just maybe we'll just use or create a new file. I'll call it Grover SLQ, and we'll start by fgrover. Come on, can my webcam just now? fgrover. First, I gotta specify that this is like. How do I make? How do I make this? That's awkward. How do I make these? Didn't just come up with a. This is the worst possible thing you can do to a developer. I'm sorry, but f. So I declare it's constant. It's got like an. How do I even do this? The arrow. Examples. Is there an example where I can just copy the arrow from? No. Oh, here. Are you kidding me? Come on. No, I wouldn't go here. So we've got like a constant then. See, that's what I mean. It's like it's taking an array of integers. That's bothering me. Exclamation mark. This is the weirdest notation I've ever seen. How do I do this Q3 here though? M3 Q3. Oh, like these, okay. So you just do Q3 and then B. How to type this? No, how to type. Maybe I can just blood type. So maybe this is just B. So I will try. What if I just use like it's otherwise so and here what if I just use that? Like, is it gonna eat it? Let's see if it eats it. Otherwise it's like and I don't care. We're gonna give it. It's how do you even call Grover? So n iterations, I'm gonna give it like just one, right? Like we'll do just a two qubit example. So n iterations is gonna be one. These things go with semicolons, yeah. Okay, so that's complaining somehow. Problems. And it's not consumed. Catch rate is constant. Instances of type not okay, but it seems to catch. No, not a type. Oh. What is not a type? This is not a type. Okay, we'll see. And then we're doing canned. What's that notation? And so this is like, this seems to be the one like this sign, but it's like 0 and then n. This n is defined somewhere, and I don't know where. Is this just pseudocode? Statements and expressions. So we're trying to build it, okay? We're trying to build it. And then 4k in 0n. Okay, so you've got the notation for including and excluding, I guess. So you've got like 4k in 0 to till n. Then you do like, so can k, you assign the Hadamard of k. Okay. Make it a bit more readable. I like these for you guys as well. There's a lot of red all over the place. That bothers me a little bit, but next is the actual iteration. So we're doing 4k in 0 n times, and then we kind of do the actual. So if can, yeah, give me a second, guys. I'll have to pause for a second. Oh, the call I had to think. Sorry. Good. Where are we? I got lost. So where are we? We're here in the main loop now. So now we're doing 4k, blah blah blah. So if f can then basically you face like face r. So this is an angle. So can I just say 3.14? That's fine, man. Doesn't look like this is anyhow. High maybe? I don't know. It's like the concept's cool, but it feels like really underdocumented, to be honest. Like, can I find in examples like face? Hey, you gotta be kidding me! Like, you can't force people to write in these things. It seems like this is all, and is not consumed. Can okay, wait a second. Good. And then we do canned. So then we do we can and we do Grover div. So this actually is really like. So this is telling how many qubits the operation is going to use. Like, oh, why is it always needed? Like, it feels it's just like, maybe I'm stupid, but it feels there's a lot of stuff wrapped around all these just to avoid talking about qubits, which I don't know if it really makes it like return measure and you don't even like, so measure. So we're not even specifying here anything in terms of, oh, so I killed all the errors. No. Okay. I guess, like, go back to the examples. So there's got to be a def main, right? Like at some point, def main. That's the entry point, and that's gonna call. I'm gonna do n equals 2, and I'm gonna call it Grover and n. And when I have to give it a function still, I don't know where we'll take it from, to be honest. It's like, at least if you go through, if you have a section that's called Grover's algorithm in Silq, like you could just go ahead and implement it as well. Have we got everything in here? But it's just all breaking. Maybe, like, do I really have to use these things? Like, let me see. Maybe I do have to use those symbols. What are those symbols called, by the way? It feels like it's a language designed so it just looks nice on papers. No? No. Okay. It's not consumed. Sorry. Now it is consumed. Come on. It is consumed. Mm. Where? It's like, where do I even start? So should I try to fix all the... Oh, iteration shouldn't be... No, I wanted to force it to be... It's not an n. Come on, it's 1. It's just a 1 iteration. N is consumed in here. N is consumed in there. Can't. It's not a type. It's not a type, but it's given here. Great. Measure, float, gravity. So why is this complaining? Parameter n is not consumed. I guess I gotta define these. Gravity, which basically seems to have the same signature. No, but it actually has canned. So it has just these, right? I guess. Gravity. Just as these parameter. Now, so I still gotta somehow quantum while. So these are loops, control flow, and safe type coercion, safe type annotation. Okay, so classical bit in 0 state. So A equals 0, and it's of type Okay, exclamation means classical. Okay, okay, good. We're learning something here. Hmm. Hmm. Exclamation means classical. So now we know why there's an exclamation here, because it refers to these, which is of type Q3. But then I don't know where. Why is the exclamation mark before? Ah, that's super confusing. B equals A, B, quantum beat in zero state. So if there's no exclamation mark, it's a quantum beat. Mm, C equals 0, U int 3. It's a quantum 3-bit unsigned integer. Okay. So, so this is not an array. Now I get it. So this is not an array, but this is an actual integer. It's just an integer that can be in superposition. Okay, makes sense. So this means this is the quantum 0 in n bits. Okay. And so, but why is it handled like if it was an array, right? Like you're accessing, okay, because you're accessing bit, like you're accessing the bit or the qubit, like this makes no sense at all. If you want to go one level of abstraction higher, like you would just do something like and equals like, I don't know, like, or even just like, can equals can proposition or something like that. Whatever. Like you just like, why you need to apply operators. Like if you want to go one level upper, then just do it. I think do it this way. It makes more sense. Oh damn! You have a vector. It's a quantum vector. So so you can have quantum vectors. So you can have a vector of, okay, a vector of quantum integers. No, of quantum beats. Okay. By default, constant values are considered classical. To create a quantum constant, Silq requires an explicit type annotation. You can create a quantum false. Okay, quantum. Okay. Writing x equals false instead of x equals false of type B in plus state results in x being classical, meaning that it is not consumed by hx. This results in the following error. So x equals false. It's a quantum false. I know it's a classical false, and so this is not consumed. Redefinition of x. Okay, yeah. Safe type conversion. Okay, we can convert types, statements and expressions. Loops, loops, loops. Assignments. For assignments, Silq also supports modifying individual vector array elements as in the following code snippet. So you've got a vector with zeros, and then you access each element of the vector and apply a harmonic gate within the vector. In general, vector array elements can be modified according to this pattern. But then this is wrong. I mean, then of course that makes no sense. That should be then a vector and not like an integer, right? Like if you're accessing this stuff like that makes totally no sense. So I would call it like I would define it like a vector of n. Can you do it like, is it length n filled with zeros, which are of type fancy, of this fancy type. constant instance type and not realizable. Cannot assign. Why cannot assign? Of course you can assign. So something's wrong with these here. Grover. Oh, so this should be classical. Of course, man, this should be classical. This code is full of errors. Okay, so this should be classical. Damn. This is. Oh, it was. Sorry. It was classical. Okay. Nice. Okay, so this is classical. Oh, that's hard. Yeah, so this is classical. So then. Okay, but then. Why is it why not a type? Why is it not a type vector? It is type. You told me it is type. Look. Look. It is a type. Okay, but like just like that. It doesn't have to be, so it can just be the number 0. So I think now I get it. Now that I've defined this as natural, as classical, now I can actually go and say that is the number 0. That is the number 0. That is a quantum number 0 made out of n qubits, made out of n beats. Yeah, now it works. Then I iterate over each of these beats and I apply the harmonic gate. And can I not can I do something like cand is equal to the harmonic of cand? Can I do this? If the argument types be, but an integer was, okay. So the harmonic expects these to be an actual quantum beat, an actual qubit. So I do have to go this way, but that feels unnecessary, as I said, to be honest. But now it seems to, okay, now it seems like there's less errors. Then we go for k, and then we just do if the function evaluates to true, then phase the state by pi. But this is still a black box for me. It's like, where is this coming? Like, what's going on here, right? Ugh. Okay. And then apply the Grover diff on these on these actual superposition. That's the thing is, what's confusing is to call this candidates, because it's simply, this is just a number. Yeah. It has the same minimum problem though, like because I'm initializing it to 0, I already know how I have to build Grover diff. But if that would be something else, then Grover diff would have to be implemented differently. Like, to be honest, you should kind of give it initial state somehow, right? Like, but it doesn't matter. As long as I hard code it, it's fine. Okay, but then how is then Grover diff working? So let's take a look at this. So this is going to be also natural, like real, okay? And so the parameter that we're given is cand, which is basically of type int n. Why isn't it? It's not consumed. Okay, so the error is that it's not consumed, but it's fine. And so we're doing this blindly because it's not. I can't find it on the web page. So what you have is basically a layer of Hadamard. So you kind of have the same thing here, right? So for each of the elements, we apply Hadamard. Then for each of the elements, we also apply a next gate, right? We will then have to. Question is now, like, with this automatic uncomputation, like, is this considered like we're uncomputing stuff? Because I would kind of like, that's not uncomputation. Although you could think of it this way. Like, because to be honest, this is what you need, right? Like, you need something like this, and then you need here the actual. So is it going here and here? It's not consumed. Oh, it's not consumed. Dude, it's consumed. Function return. What is this returning, by the way? Canned. So this is like return canned. Okay. And so here you kind of have the. It's just going to be a control set, right? Because we just have 2 qubits. So we're just going to hard code it here. I know that I'm going to use n equals 2. I'm not going to. Okay, but I need to specify this is a natural. This is a natural. This is this. Natural. It's a classical thing. Like that type. And I'm still missing F, right? So what's F? I'm still missing F to be able to call this. And and this kind of returns something, right? Like an M. And so I don't know how to print that. Okay. But Grover diffusion operator would be. So in this case, how would you do a control Z? Because it's an if, right? So but like you do have to make reference to the qubits, right? Like, oh, I can just say if. I can just say, can I just say if can equals, like, how do I compare, like 3, right? Because it's the 1 1. That makes it so weird. That is so weird. What I'm trying to do is I'm like, because what the controls that does is it flips the state 1 1, right, which is 3 binary. And so phase phase pi. But that makes no, like, that is the opposite of being intuitive. An identifier. Okay, yeah, the F is not, but it's not complaining. Interesting. That can't really work. We'll try to debug this thing. But now, how do we build F? Nice. So, I guess F is a function, right? So I guess we kind of define it as well like that, like F. So F has something of this type, and it returns a classical Boolean, right? So F would be ff, like takes like it takes these. It's the same like doesn't need to know that it operates. It also needs to know that it operates in n qubits, because otherwise there's no way that this works. I mean, now let's say if and work. Assuming that this is the equality, because if can equals, so we're looking for number one, say, right? Then phase. Okay. So this could just be that. And then we return. No. So all we do is return can equals 1. Okay. So that's all we do. It's not consumed because it's const. How do we do this? Invalid const annotation. Candidate is const. Is a constant. So constant meant the authors of the creators of this are probably, if they're probably watching, they're like, what the hell is this guy doing? It's an aberration. Const. Where's the problem with these candidates? Const. Oh. So it returns, like, I think there's something you have to do like these, right? That it returns a Q3B. The strafe. Why? Examples. State B. I don't know, like these. So QS, and then it returns something. Any examples? Where can I find Silq examples? How do I declare these? So aim free. Okay, so this is the type is the class, like these. So first goes Q3 and then goes this. Oh, no. Okay, so returns a Q3 is type. Q3 is a type as well. So I don't really. So whatever is after the semicolon is the correct type. Const. So it'll be const. What would these be then? How would you do that? F of type const and then expression. So const type of type what? Int n, which is basically just that, int n. Valid const. Can you explain me? Oh, can I just do? So what is in here? Const. Okay. So const. So const goes here, like telling me the candidate is constant, and I say it's of type int. Oh, okay. So I don't know. It's really confusing why this goes before, because here we have variable name and then I'm just stupid, I guess. Okay, and so here we expect types const int q4b, but const uh, 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 so we expect of the type expected argument types const int blah blah blah, but instead we're giving some weird stuff. Okay. Maybe this is, yeah, this is not needed. Yeah, but then how can I even define that? So I just, so just int type, let's give it like this. You know, I'm kind of missing, like, how do I just hard code these? Or can I just use that? But then I don't have n. I know. I do this probably. So I've got the scanf of this type. And so what if I give these back here? Yeah, okay, that works. So I tell f that it needs to operate on n qubits, but I also gotta give it the n when I call this. This n is kind of annoying, but it's gotta be there. So we set it to 2. Okay. So that now has no errors, no syntax errors, apparently. What do I do with it? Main. So the main returns something as well. Okay. So I can just return then, I guess, these, right? So I can just return me Grover. Local variable n appears in function return type. And what? I do n equals these. Return n. Probabilities now. Local variable n appears in function return type. Grover. Oh, I mean, I don't get it. I don't get it. How do I print these? Check, check. Check, check. So do I have to return like these or what? Solve and solve. And so what is it doing here? Solve, and this returns measure. So returns. What is Grover doing? I'm so lost. Where's Grover? Here. Return measure can. And what? Maybe I'm missing the point of all these, but like. Return y. Return y. What am I looking at? What I'm really in M3 context. Local variable appears in function return type. In what function return type? Main, return implicit measurement. Return Grover. Grover has no return thingy defined. So if I just do this, okay, that breaks, that kind of does the same. I saw this in one of the examples, but I don't really know what it means. Return Where did I see this now? Here in some of the examples. Return measure. And so then you're checking. Okay, what about we just don't return anything, and we try to inspect maybe what's in there somehow. So I saw here somewhere like debugging. Dumps the current program state when running the program. Let's do that. So we'll dump before Grover. We'll dump after Grover. Let's see what happens. Okay. Here we go. How do I run these? No, how do I run these? So I have to. How do I run these examples? Comparison, Silq, overview, install. What was that? Installing Silq. I think it was explained here. VS Code. And how does it run? Oh, look! It looks like this should work. You can use B and N and stuff like that. Because here I see it in the code. Let's try right away. So let's just use these more convenient notation instead of these fancy things. Just because it's more close to what normal human beings use, to be honest. And how do we run these? Run type check, no, run program. Command Silq. How do I run it in? Programs the main function can be run by pressing F5. Okay. Ooh. Okay, so variables m equals -1, n equals 2. Okay, so that dumps the state of the program. Quantum state. Okay. So what is it doing? So we've got a quantum state, which is, isn't there missing something here? What is that? I guess it's 0. Like if I don't do this, then if I just do one dump at the end, this is the quantum state that this whole thing has. Let's do step by step. So let's dump stuff and let's see what happens. So we're getting to Grover. And we're getting to Grover and we go through. So now here we should have a superposition, right? Let's see. Oh, because this is because it's a signed integer, so it's oh, that's funky. So this should be, I will use uint because then it's gonna help me better see how things are going, because with an unsigned integer, then I'll go from 0 upwards. Yeah, good. Yeah, here we go. So we have a superposition. Okay. What does the little 0 mean, though? I don't know. And here we have a bunch of other stuff. I don't know what's frame and outer. I don't know. But we have this quantum state. Good. Now, after we have applied the phase, now this is wrong. This is not. This is n iterations. by the way. 10 iterations, which kind of just will happen once. So if we dump right after that, we get this. We get this quantum state, which is -1 on the 1 state. Does this make sense? What is our f doing? Yeah. What if I say that our f, please do these, face this element? Oh, but it should be a superposition. That's almost 0, right? So we ignore these. Let me see. Yeah, so it looks like it's phasing just that state. But what about the rest of the quantum state? It cannot just be all. It cannot just be all. Oh, it's applied Grover because it applies the Grover. Okay, so let's see if we don't do these. Okay, what happens? Okay, here we go. So it actually, oh, it's nice because you see the plus and you see the minus. So it actually phases that element. So I guessed how to actually be F. Nice. Nice, nice. Good, 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 good. If candidate is 2, right? If the parameter is 2, but we're giving it a superposition in reality. So if candidate is 3, should see 3. What if I say quantum is 4? Is this then gonna do probably nothing? Yeah. Okay. If I say 4 end, or it's like end candidate equals 3, work as well? Ooh. End. Oh, end or. uh, uh, yeah, come on, baby. It works. Okay. So I guess you can build, this is your oracle, right? This is kind of your oracle. And it's kind of as easy as you don't care. You really don't care. Like, truth be told, it's like you can define the oracle independently. I mean, this seems to be a bit useful, right? Because you don't like, okay, I need to put like a control, multi-control, whatever. You're just literally saying, if this is satisfied for within your superposition, and can gives you, like, you have the superposition in there. You can do whatever you want with it. Like, you can operate on it as if it was a number. For example, what if I say, okay, so let's say, for example, that we want to do this for if candidate, like, is this going to work as well? Modulo, like, 2 equals 0. What does this give me, for example? That's cool. So the even numbers. Nice. Okay, that's interesting. That is indeed interesting. But it's not going to, if I have just 2 qubits, what if I say 3 qubits? Okay, so what if I give it 3 qubits? Do I have to change something? Or is it going to work out of the box? Worked out of the box. That's nice. So now we have got the even numbers phased. But I think it's already too much, right? Like, too many of them, right? Like, that's the problem. So if I just like do something like that, how many of them is going to? Okay, so let's just phase these, right? So multiples of 3 in this case, yeah. Okay, cool. So the oracle works. That's pretty nice. And now let's see what happens inside the diffusion operator. And inside the diffusion operator. So what this does here now is, So I guess if I dump here, I'd be able to see for every iteration, right? It's just going to be one. I'm getting to see the transformation step by step. Like my question is, actually, if I just dump at the end now, what do I get? What's the state that I get in? It's a weird state. I mean, m equals 6. Okay. If I run it again, whoopa. It's always, oh no, okay. So it's actually not deterministic. Actually, I should run this many times. It gives me different numbers every time. Okay. How can I sample this? But it seems to work well, does it? I mean, at the end of Grover's diffusion operator, this is, I'm not sure this is kind of, okay, that's definitely not correct now, because that should be now 7, right? Because now we're going to face this one. This is what's kind of still, I think I'm going to leave this one. This is what's not clear to me yet. Like, that's super unintuitive. Like, if you have to build this way, why the candidate 7, right? Like, if all what you're doing is you're correcting, why that candidate? Unless you understand the inner workings of these, the way of implementing the diffusion operator seems to be the same. Like, that doesn't seem to change with the language, with Silq. Okay. Because if I give it a, if I dump here, what do I see? What if I just for the sake of making these easier to see, I will make f to just return equals like 0. Okay. Okay, yeah. So this seems to work. No, yeah, this is way bigger, right? Like than everything else, because it's 0.8 and everything else is 0.1. Yeah. Whereas if I put a 3 here, it's going to do some weird thing. Yeah, that's a weird thing. It doesn't work. Let's try. If I initialize this to 1, and now I do like 7, and I remove these things, that should also work, right? Ugh. Do what I expected to do. That's interesting. Okay. Because to be honest, I expected these to give me the same, like how I had it before. You know what I mean? Because it depends on how you initialize the state. Like, check out my other Grover videos. But if you oh no, not 1, of course, not 1. That would be not 1. That would be 7, right? Yeah. So if we initialize with all 1s, that's what I want to check. And then we don't do this. Yeah. But it's still, there's got to be a better way to build that. Okay, so we'll probably explore this in the next video. I'm kind of happy because I really figured it out. I feel I almost figured it out. I see the advantage in building these kind of oracles, or at least in working with superpositions. But I don't like two things. I don't like. I mean, okay, if you assume and you work with the concept of my program has one single state that I'm working on, then it makes sense to have these types of functions that affect the global the phase of the whole thing, unless you condition it, right? Because if you don't condition it, then it's just a global phase that you're adding. It adds a phase to the whole state. That's the point. So that kind of is nice. This I don't like. The way you create superpositions, this feels really still low level. Like, it's just too low level. I like that you can define an actual unsigned integer as a quantum concept, as a quantum thing that you can then, have it in superposition. But the fact that you got to dive into its actual bits to create superposition, that feels awkward. That feels low level. There should be just an operation for that, I think. Anyway, that's probably already too long of a video, but cool. Yeah, I'm happy. I think this got a lot of potential. We'll explore farther because I still have some of the stuff that I'm not really sure how to test things, how to make them work correctly. But it's an interesting language, and I think once I figure those things out, I'll try. My next challenge will be build a quantum Fourier transform with these. That's gonna be a nice one. Yeah, hope you liked it. And I don't often say this, but if you enjoy these videos, please subscribe. I always like to see the number go up. It makes me happy because it kind of tells me that people enjoy the content. And yeah, I think that kind of keeps me pushing hard on this. Yeah. And stay tuned for more stuff to come. Quantum Dojo tournament coming soon. A lot of new puzzles and a bunch of other things coming up on the channel as well. And I'm going to be really trying to close up a lot of the open topics that I've opened. It's a bit of a mess right now, but bear with me, please. Okay. Cool. Then see you next time.